This is Chapter 4. There's a lot of information here, so I'm going to break my video series into two parts. This part will talk about hardware. There's a little bit of extra information in this video that's not in the text, but I think it's important for us to gain as much knowledge about hardware and software so that we know what we're talking about when we get into our careers, whether we're going to be in the IT field or as a professional that simply uses computers. A computer is an electronic device that can take inputs, process them, output the results, and store those results for later use. This is a neat definition because it allows for a computer to be more than just the thing that sits on top of your desk. A computer can be a tablet, a smartphone, or even a programmable thermostat. The information processing cycle is a model we use to show how different hardware components work together. Everything starts with input devices. An input device is anything you use to put data into a computer. Things like cameras, scanners, mice, keyboards, or microphones. All this data is converted into a digital format and sent to memory. Digital data is represented by bits. A bit is a 1 or a 0. Computers are machines that only understand two states. There's either a charge or there's no charge. There's either a positive magnetic polarity or a negative one. Light is either reflected or it's not. When you group 8 bits together, you have a byte. A byte is roughly equivalent to a character. The word byte would be 4 bytes since it has 4 letters in it. Once you have 1,000 bytes, you have a kilobyte. A megabyte has 1 million bytes. A gigabyte has 1 billion bytes, and a terabyte has 1 trillion bytes. If you want to get technical about these prefixes, a kilobyte is actually 1,024 bytes, and a megabyte is actually 1,048,576 bytes. These numbers come from the binary system. Since there are only 2 states, on or off, prefixes are based on a base 2 system. So a kilobyte is 2 to the 10th, or 1,024 bytes, if you multiply that out. A megabyte is 2 to the 20th, or 1,048,576 bytes. A gigabyte is 2 to the 30th, and a terabyte is 2 to the 40th. There are other units past a terabyte, but at a consumer level, we won't ever deal with petabytes or exabytes. Those are usually terms used on servers or when dealing with lots of data. When a computer works with data, that data has to be represented by ones and zeros. Random access memory, or RAM, or just memory, holds all these ones and zeros until they're ready to be processed, and memory holds the result of that processing. Memory is measured by how much data it can hold. Typically, you'll hear computers with 4 gigabytes or 8 gigabytes of memory, while some higher-end ones may have 16 gigabytes. This capacity is important in the grand scheme of things because it relates to how much you can do with your computer at once. Think of memory as the space on your office desk. You're limited by the surface area on your desk in laying out different reports or having post-it notes everywhere, along with your pens, calculators, and coffee mugs. If you run out of space on your desk, your productivity slows down, and you'll have to move stuff off your desk to make space for more stuff. But if you have a larger desk, you have more space for more stuff. The same goes with memory. If you have 4 gigabytes of memory, that limits how much data you can input through your cameras or keyboards. When you have different programs running, that uses memory as well. So if you find your computer is running slowly when you have 6 browser tabs open while streaming Pandora and working on a PowerPoint presentation, you may have to close some of the things down. Your computer can't handle all of that because its desktop space, or memory, is limited. The alternative would be to get a bigger desk, or to increase your memory, which actually isn't a hard upgrade to perform if you want to try that yourself. You may hear a lot of terms when talking about memory, such as SODIMM, which is Small Outline Dual Inline Memory Module, or DDR, which is Dual Data Rate. A lot of these will be specific to the computer you're using. For example, laptops use SODIMM memory because of their size, and some computers can only use DDR3 memory and not DDR4. If you want to upgrade your memory, visit a site like Crucial.com, put in information about the computer you're using, and the site will tell you exactly what you need to buy if you want to upgrade your memory. Your central processing unit, or CPU, or just processor, is responsible for making sense of all the bytes of information that's sitting in memory. Computer processors are generally made by either Intel or AMD. The i3, i5, and i7 processors are made by Intel, as are Pentiums and Celerons. AMD makes Ryzen and Athlon processors. These have slight differences in the way they do things, and in a business sense, for the most part, it doesn't really matter which brand you use. At their core, processors do the same thing. They grab some data from memory, process it, and put it back into memory. But there are a few specifications worth noting. The amount of data a processor grabs from memory is the word size. A 64-bit processor grabs 64 bits of data from memory every cycle. This is different from 64-bit programs. A 64-bit processor can run 64-bit or 32-bit programs, but a 32-bit processor can only run 32-bit programs. CPUs are sometimes noted for how fast they can process things. Hertz is a unit of measure that represents a cycle per second. When a processor gets data, processes it, and puts it back into memory, that's one cycle. CPUs can go through this cycle many times per second. If you ever see a processor described in hertz, such as a 3.6 gigahertz processor, that means the processor is capable of the get, process, put back cycle 3.6 billion times per second. The prefixes for processor speeds are the same as with memory capacities. Kilo is 1,000, mega is 1,000,000, and giga is 1,000,000,000. A CPU is made up of a control unit and arithmetic logic unit, which, when taken together, are the core of a CPU. Modern processors usually have multiple cores. If you see a processor advertised as a quad-core CPU, that means it has 4 separate control and ALU pairs working in tandem with each other. Once a CPU has processed the raw bytes that came from your input devices, your computer is ready to output that for you to use. Output devices include monitors, printers, speakers, or even vibrating motors like the Taptic engine in iPhones. If you need to keep data for use later, use a storage device. Storage devices consist of optical drives, floppy drives, hard drives, and solid-state drives. Capacity for storage devices uses the same terminology as memory, so you'll hear drives as having 256 gigabytes or 2 terabytes worth of storage. Floppy and hard drives work on magnetic principles. The disks themselves have magnetic particles that are oriented a certain way so that when a read-write head passes over them, they represent ones and zeros based on the polarity that the read-write head senses. Optical drives work by reflecting light back to a source. Data on optical disks are arranged in a spiral like vinyl records. A laser shines on the surface of an optical disc, and if it's reflected, that particular spot represents a 1, and if it isn't reflected, then that spot represents a 0. Solid-state drives work by using flash memory chips, the same kind of chips in your USB drives. SSDs are becoming more popular nowadays because they are faster than traditional hard drives, and because they don't have any moving parts like a hard drive does, they're more reliable. However, they're still more expensive than hard drives on a per byte basis. A 1 terabyte hard drive may be selling for $45, but a comparable 1 terabyte solid-state drive may be selling for $115. Sometimes people refer to memory as primary storage and hard drives as secondary storage. This makes sense somewhat since both store data. The only difference is that memory stores data that the CPU directly accesses, and hard drives store data that is passed along to the CPU through memory. You might also hear RAM being referred to as volatile and storage devices as non-volatile. RAM needs a constant source of power to maintain the data stored on it. Without power, the data on RAM is lost. Storage devices don't require power to store data. Yes, they require power to write the data, but once the data is written on the drive or stored on the flash chips, they don't require power to maintain that data. And that's the hardware portion of Chapter 4.